that we have found a new particle never seen before in Mother Nature. By slamming two beams of proton at trillions of electron volts, everything we see around us, the galaxies, the planets, the Earth, life itself, is a byproduct of an explosion which was set off by a Higgs-like particle.
Alain Blondel, a particle physicist who has worked at CERN and the University of Geneva in Switzerland. The science we do, together with cosmology, astrophysics, and many other fields, explores how the universe was born and how it works. These are questions that have fascinated people for generations. In recent months, the European Organization for Nuclear Research, CERN, has witnessed a series of baffling events that have left both scientists and the public in a state of curiosity and concern. While the precise nature of these phenomena remains shrouded in mystery, they underscore the complex and enigmatic nature of particle physics and the need for further investigations. Home to the Large Hadron Collider, LHC, has always been at the forefront of groundbreaking discoveries in the world of particle physics. However, the current situation is something entirely different. Over the last year, scientists have observed inexplicable fluctuations in experimental data and unanticipated anomalies in their particle acceleration experiments. In this video, we will discuss a new discovery of CERN that changed the human mind about the discovery of the universe. So don't go away, stay with us and keep watching our channel, and also subscribe our channel. The Large Hadron Collider. The Large Hadron Collider is the world's most powerful particle accelerator. Protons are circulated in both clockwise and counterclockwise directions, where they'll eventually be forced to collide. Roughly 100 meters underground, in a tunnel that crosses the border between Switzerland and France, lies the largest machine ever built. The Large Hadron Collider, LHC, compresses and collides tiny bits of matter to recreate the fundamental particles that appeared just 1/1,000,000th of a second after the universe was created. The LHC consists of a 27-kilometer ring of superconducting magnets with a number of accelerating structures to boost the energy of the particles along the way. The cost of LHC is $5 billion. That's a huge amount of money. This huge investment wasn't just footed by CERN's 23 member states. It attracted contributions from countries far beyond Europe, including Japan, Canada, and the United States. Because the discoveries made at the LHC aren't just relevant to Europe, they're a forward step for all of humanity despite its promising potential. The LHC can reproduce the conditions that existed within a billionth of a second of the Big Bang. The colossal accelerator allows scientists to collide high-energy subatomic particles in a controlled environment and observe the interactions. One of the most significant LHC breakthroughs came in 2012 with the discovery of the Higgs boson. Although widely referred to as the God particle, it's not really as awesome in itself as that name might suggest. Its huge significance came from the fact that it was the last prediction of the Standard Model that hadn't yet been proven. But the Higgs boson is far from being the LHC's only discovery. As huge as it is, the LHC can't function without the help of other machines around it. Before particles, which are usually protons but for some experiments are much heavier lead ions, are injected into it, they're passed through a chain of smaller accelerators that progressively boost their speed, according to a CERN LHC report. Smaller is just a relative term. The last step in the injector chain, the superproton synchrotron, is almost 4.3 miles in circumference. Inside the accelerator, two high-energy particle beams travel at close to the speed of light before they are made to collide. The beams travel in opposite directions in separate beam pipes, two tubes kept at ultra-high vacuum. They are guided around the accelerator ring by a strong magnetic field maintained by superconducting electromagnets. The electromagnets are built from coils of special electric cable that operate in a superconducting state, efficiently conducting electricity without resistance or loss of energy. This requires chilling the magnets to 271.3 degrees Celsius, a temperature colder than outer space. For this reason, much of the accelerator is connected to a distribution system of liquid helium, which cools the magnets, as well as to other supply services. A particle explosion. When these particle collisions happen, the result is a shower of particles, whizzing out in every direction. Most of them only stay in existence for fractions of a second before decaying out of existence. Varying the types of particles, researchers can help discover new particles in these flurries. With the help of specially designed, super-sensitive detectors are placed around the collision sites to capture all the information from each and every collision, and this amount of information really adds up and requires a huge amount of time and manpower to sift through. Experiments at the LHC create more than 15 petabytes of raw data from these collisions every year, which then need to be meticulously combed through to sort out the data the researchers are looking for. Back in 2017, the LHC surpassed a major milestone when they had put over 200 petabytes of data permanently into its tape libraries. To put this amount of data into perspective, 1 petabyte of data is equivalent to around 250,000 movies. Quark. They noticed something going on with a particular kind of quark. Quarks are the building blocks of all matter and come in a variety of types that physics call flavor. There are 6 types known as flavors of quarks: up, down, charm, strange, top, and bottom. Up and down quarks have the lowest masses of all quarks. The heavier quarks rapidly change into up and down quarks through a process of particle decay. The beauty quark, which has an average lifespan of 1.5 trillionth of a second, was the subject of this particular anomaly when its decay pattern was different from what scientists predicted. Based on the standard model, these particles have unique decay patterns that help scientists investigate potential physics beyond the standard model, leading to groundbreaking insights about the universe. Make-up Z-prime particle. The Z-prime particle is a theoretical heavyweight in the world of particle physics, as a proposed heavier cousin of the Z boson, which mediates weak nuclear forces. The Z-prime could unlock answers to deep puzzles about the universe's fundamental forces. What is the Higgs boson? Detecting the Higgs boson isn't just a question of setting up a detector and waiting for one to come along. These particles only existed in the high-energy conditions of the early universe. That means before detecting this particle, these high-energy conditions have to be replicated, and Higgs bosons have to be created. The LHC does this by accelerating protons to near-light speed and smashing them together. This creates a cascade of particles that quickly decay into lighter particles. The Higgs boson decays too rapidly to be spotted and was instead identified by detecting particle decays that indicated a particle with no spin and matched theoretical predictions for this missing boson. The new particle discovered by the International Atlas and CMS collaborations in 2012 appeared very much like the Higgs boson predicted by the standard model. But was it actually that long-sought-after particle? As soon as the discovery had been made, Atlas and CMS set out to investigate in detail whether the properties of the particle they had discovered truly matched those predicted by the standard model. By using data from the disintegration or decay of the new particle into 2 photons, the carriers of the electromagnetic force, the experiments have demonstrated that the new particle has no intrinsic angular momentum or quantum spin, exactly like the Higgs boson predicted by the standard model. By contrast, all other known elementary particles have spin. The matter particles, such as the up and down quarks that form protons and neutrons, and the force-carrying particles, such as the W and Z bosons. By observing the Higgs bosons being produced from and decaying into pairs of W or Z bosons, Atlas and CMS confirmed that these gain their mass through their interactions with the Higgs field, as predicted by the standard model. The strength of these interactions explains the short range of the weak force, which is responsible for a form of radioactivity and initiates the nuclear fusion reaction that powers the sun. Atlas and CMS measured the Higgs boson's mass to be 125 billion electrons, GeV, with an impressive precision of almost 1 per mil. The mass of the Higgs boson is a fundamental constant of nature that is not predicted by the standard model. Moreover, together with the mass of the heaviest known elementary particle, the top quark, and other parameters, the Higgs boson's mass may determine the stability of the universe's vacuum. By revealing this particle, predicted by the standard model, the discovery of the Higgs boson completed this picture of the subatomic world. There are still mysteries beyond this theory, such as the nature of dark matter, which the Higgs boson, through its unique properties, could help solve. The God particle. The Higgs boson's nickname, the God particle, was solidified upon its discovery, namely as a result of the popular media. The origin of this is often connected to Nobel Prize-winning physicist Leon Lederman, referring to the Higgs boson as the goddamn particle in frustration with regards to how difficult it was to detect. Business Insider says that when Lederman authored a book on the Higgs boson in the 1990s, the title was to be The Goddamn Particle, but the publishers changed this to The God Particle. This name sparked many debates about the link between science and religion. The importance of the Higgs boson and its field is huge. Without them, particles wouldn't have mass. Without mass, there'd be no galaxies, stars, planets, or life. This is why the nickname, even if dramatic, highlights its importance. Scientists are still studying the Higgs boson to understand the early universe and how it stays stable over time. The Higgs field is special because it gives a baseline energy to the vacuum of space, which is crucial for the universe to exist. Scientists think that by understanding this field's energy, they can explain why the electromagnetic force has an infinite range, while the weak force doesn't. The Higgs boson, after 2012. The year after the discovery of the Higgs boson, Peter Higgs and Francois Englert were awarded the 2013 Nobel Prize in Physics for their Higgs field theory. The Nobel Committee wrote of the award, "For the theoretical discovery of a mechanism that contributes to our understanding of the origin of mass of subatomic particles, and which recently was confirmed through the discovery of the predicted fundamental particle by the ATLAS and CMS experiments at CERN's Large Hadron Collider. The discovery of the Higgs boson may have completed the standard model, but this wasn't the end of the investigation of this elusive particle. One of the major discoveries made since 2012 has involved confirmation of the decay of the hexane. The investigation of this elusive particle will deepen during Run 3 of the LHC, and particularly when the particle accelerator's high luminosity upgrade is completed in 2029. This will allow the LHC to conduct more collisions, providing researchers with more opportunities to spot exotic physics, including phenomena beyond the standard model. CERN estimates that following the upgrade each year, the accelerator will create 15 million of these particles. This is compared to 3 million Higgs bosons created by the LHC in 2017. This may be key to detecting other flavors of the Higgs boson. Theories that go beyond the standard model of particle physics also predict as many as 5 different types of Higgs bosons, which may be produced more infrequently than the primary Higgs boson. Even before the upgrades, scientists have already provided us with tantalizing evidence of a magnetic Higgs boson. We hope you liked the video. If you did, please give us a like, share, and subscribe to our channel for more videos like this. Don't forget to leave a comment below. We would love to hear from you. Thank you for watching and see you next time.